Okay. So first question. What's the first question here? Numero 4? Yeah? 6? Oh, I thought it was 4. 4. I think so. From the other day. I think it was 4 or 5, wasn't it? No, it started 4. Yeah. Yeah, I gave you extra questions. We started 4. We didn't go over 4, did we? No. No. We start with 4. Okay. Now, we're going to compare these molecules basically. So take a look here. Those, okay? Now, sometimes, I guess maybe I'll mention this real quick here. It basically says, take a look at these 4 molecules, organize them in terms of, explain their differences in their boiling points. So, who's going to explain their differences in boiling points to me? Where are we going to start? I think. Somebody. Well, you guys have all this homework done, so you tell me. Before we start talking about boiling points and melting points and all that stuff, we have to figure out what kind of forces we have here, yes? So that's step 1. And of course, if we're going to talk about boiling points or melting points or how well they stick together, we use that chart. Are these ionic compounds? Yes or no? This one's probably close, right? That's not. I know that. No, how do you know? How do you know? Oh, come on, you got to know this. We talked about this already. I gave you heck for not knowing this already on a quiz. Yeah. Yeah, subtract the electronegativities, right? This is like 1.8. That's like 1, I think. I don't think that's ionic. You know, this one might be, but we pretend it's molecular in most cases. We'll talk about that in a second. This is like that difference isn't too big for HCl, right? So we talk about what kind of molecules do we have here, right? Are they ionic? Maybe, but probably definitely not for those. Are they metallic? Are they just metals? No. Are they molecular? Do we have nonmetals? Yes. Is this hydrogen bonding? Yes. So this is hydrogen bonding. Is that HCl? Is that hydrogen bonding? No, it's dipole-dipole. Dipole-dipole, dipole-dipole. I mean, guys, anytime you're comparing I should have everybody's hands should be going up here. If you don't know this, we're in trouble, okay? We have to know if we're talking about melting and boiling points, they're asking you about the chart. Where do these slot in? Look, we got 4 molecules. Where do they fit into? That's what we're doing, okay? You got to know the chart. You got to know what kind of forces we have here. Then, this is hydrogen bonding. This is actually exactly off the chart. We've already done this. Well, we didn't do this one. I ignored it, but that was on the chart from the Google Classroom thing there that we talked about. We did this. Then how do I decide between the dipole-dipoles? Which one's the strongest? Which one's the weakest? You guys know this. What is it? Tell me, somebody. Please talk to me. Otherwise, I'm going to stay home tomorrow. Oh, you want me to stay home tomorrow? I see. I get it. Okay. I thought we had something, but apparently not. Okay. You know what? Hey. Hey. She's ignoring me. How do you know? No. Yeah. No. Yeah. Yeah. Number of electrons. Actually, I'm super happy you said that. Really happy. That's why I like you so much. Size of electrons, yes? Okay. How many are going to be here? I think this is what? 18, 36, 54, yes? So we know that those increase, like, do you remember this chart? Remember this? And then hydrogen bonding, stronger, yeah? Now, is it higher than all those? I assume it is. I don't know for sure, but I'm going to assume it is because that's the chart we have. And that's basically what they're asking you. This would be this is only 10 electrons, but it's got hydrogen bonding, so it's stronger. Yes? Okay? Okay? Now, I'm going to pick on you for a second, and I'm glad you said that. Listen, when we compare, listen close, I hate to even say this again because people hear this and then use this on the test, and it really upsets me because this is never the answer. No offense. This is never the answer. Okay, people talk about, well, this one's more polar because it has a bigger difference in electronegativity. Have we ever compared a molecule based on electronegativity differences? We base it on what? Size, shape, dipole-dipole, hydrogen bonding, ionic, yes, metallic, yes, chart, yes. In that chart, there is no mention of difference in electronegativity. There never will be. We will never do that, okay? That is not an option. So electronegativity is not the answer. When you're comparing boiling points, melting points, strengths, which one's the strongest? It's the ionic metallic for the 100th time now. Molecular, hydrogen bonding, dipole-dipole, unforced size shape. That's what you compare them based on. That's the only answers, okay? So we don't talk about anything else, nothing else ever again, okay? If you want to decide which bond is more polar, then yes, I think there's a question like that there. Yeah, absolutely. You can decide, oh, which one's got more of a negative end and a positive end. Yeah, absolutely. You can do that. That's in there somewhere, maybe coming up in the next couple of days here. Yeah, you can do that. You can organize them based on that for sure. But that doesn't mean the molecule's any stronger. Okay. All right. Next. What are we doing? 5? So first of all, when they talk about a permanent dipole and a induced dipole, they're talking about polar versus nonpolar. What's the effect on melting points? So basically they're talking about, and it's never a bad thing, hey, let's compare those two. What is the difference between polar and nonpolar? We talked about permanent dipoles, yes? Okay, so these are always on. Why do these have permanent dipoles? These are temporary. Why are these permanent? Yeah, no, somebody else. Why are they permanent? Abby? Why? Yeah, absolutely. Why? Exactly. Difference in electronegativity, yes? Okay. So we always have a negative end, we always have a positive. I'll give you a quick little example here. Okay. 3.2, 2.2, those don't cancel. Partial negative, partial positive, yes? Those are permanent dipoles. They're always there due to a difference in electronegativity. What's a nonpolar temporary dipole? Somebody else. Dylan? They are. In this case here, right, electronegativity is the same, right? So we don't have a permanent negative and a permanent positive end. For example, this is the one I gave you in class, 2.2, 2.2, they pull evenly. So which way do the electrons get pulled? Well, they're shared equally, yes? I mean, these are very simple nonpolar molecules, but that's okay. And because of that, they form temporary dipoles, which is really based on what now? What are the temporary dipoles based on? Come on, somebody. Ben. Ben. Something. Electrons. Going and around and yes, electrons going around and around, yes. So when electrons go around and around, at some point we get a little bit, we get maybe 2 electrons over here, we get a little bit negative. and a little bit positive, yes? And that's the difference. Remember, those also turn off though, yes? And they also switch, right? So that's the induced dipole thing, right? That's what they're talking about here. Those are two big differences. What could I change here? What would I say if I wanted to talk about polar? What else could I write there? We've done this over and over again. We just did it on a quiz. Instead of putting polar there, what else could I put? I had a quiz on it. You put polar, you put, yep. No. Dipole. There's another way to say that, yes. Dipole. Maybe hydrogen bonding, but that's a pretty extreme case of that, but that, I guess, true, okay? And here I'd put London, right? What if you had to compare dipole and London forces? Well, that's what they're based on, right? One's polar, one's nonpolar. So that's the difference, yes? And it's a little bit more than that, but I think for this question, that's probably good enough. But you'd want to talk about perhaps maybe permanent dipoles. Why is there? Due to a difference in electronegativity, right? Electrons spend more time around the electronegative atom, so that's always going to be your negative, partial negative end, and then that leaves the other part partially positive, okay? All right, that's 5, I guess. 6, I gave you 6 eventually here, yes? Well, okay, which one's higher? What's the effect on the boiling point then? Which one's higher? Polar. Should be higher, yes? Because it's always a negative and a positive end. The other ones are temporary, right? So they're not going to last as long. Usually these ones will be lower. So this will have a higher boiling point. This will be lower. Okay, good. Okay. 6. This is exactly what we're talking about here. This is nonpolar, and it boils at 200. Well, actually above 200, somewhere above 200. Water boils at 100. Does that make sense? Would we think that that's actually true? In most cases, would we believe that that's true? Yes or no? Just looking at those two. Well, does that make sense to you? Water's what kind of bonding do we have here? Again, we're talking about melting and boiling points. So we should be talking about what? Intermolecular forces, yes? The chart. Water has what? Yep. So this hydrogen bonding, is hydrogen bonding weaker than London? Because that's what they're asking you, right? True or not? No, we would expect hydrogen bonding to be stronger. So they're saying, hey, this doesn't follow the pattern. Why? And of course, I think I already told you about this, but what's going on with the nonpolar compound here? It has to be what? Yep. Yep. Which means what? Absolutely, it could be. Cooking oil is, but what does that mean for the for nonpolar London here? Yeah, absolutely. Long carbon chain, perhaps. Yeah. What else? Really, we got to look at the chart. What else? Come on. Come on. Yep. A lot of electrons or shape, right? This has to be really big in size. So maybe a really long carbon chain, or maybe it's very linear, or maybe it's both. I don't know, okay? But obviously there has to be so many electrons there. This comes back to the chart we did the other day, where dipole wasn't stronger, or was stronger than the hydrogen bonding because it had more electrons, okay? So it has to be size and shape based on that, yep. You should have both, because you don't know if it's size or shape or both, right? And London forces are based on those two things. So yeah, you probably should mention both for sure. Yep. Okay. What's next? 7. Okay. Now, it said, now I know this is already a gas. I get that. But basically they're saying what kind of forces are involved with these compounds. So if I wanted to, let's say we had solid NH3, what would I have to break in order to change it to a liquid and into a gas? What's the best force that describes this compound basically? That on that chart, it is what? Hydrogen bonding, yes? Okay. The next one is NAI. This is 7. What's the best force to describe that? What do I have to break in order to change this from a solid to a liquid? What is the force here? Yep. What's that? I didn't hear you. No? No. Yeah. Huh? No. Guess again. We're 0 for 0. Yep. Yeah. Isn't it ionic? A metal and a non-metal? Last I checked. Yeah. Look, it comes down to the entire chart. That's why we did this one next. What about iron? What do you have to break in order to change iron to iron to iron to iron in order to make it a liquid? Yeah, it's metallic bonding. Right? It's a metal, right? Those two would be the highest, would you not? Yes? I don't know which one's higher. I don't know, but they're both pretty darn strong. Okay, I gotta be careful what I say here. CH4. What kind of forces do we have here? What do you have to break with this? Again, you look at the compound, you decide, what is it? Okay? Right. No. London. AX4, non-polar. London. Okay? So you're breaking London forces there. Okay, good. All right. What did I give you next here? 11? What's dipole, dipole, and ionic? So compare to ionic. Never a bad idea if you ask to compare two things, make a little chart. Okay, there's nothing wrong with that. You don't have to write everything out. Make a little chart, make some point forms, but just be precise with it, kind of thing. What's the difference between dipole, dipole, and ionic? What's the first thing? Yeah. Yeah. This is molecular, which if you want to summarize that, you'd say what? You know, even more based. That's great. That's I want to hear that. What's the first? You would say what? Molecular is made up of what? Yeah, non-metals. So if you want to put that in there too, that's fine. Perfect. Okay. What about ionic? We know that this is, well, ionic, yes, I guess, which of course you'd have to talk about metals and non-metals, yes? Metals and non-metals. So I guess over there, probably to compare the two, you'd probably put non-metals, non-metals, yes? I guess that would make sense. Okay. What's next? What does it really depend on? And we've already talked about it today again. What is the difference between an ionic and just a dipole-dipole? That is the biggest difference here. You absolutely need to have something about there's a difference in electronegativity, right? This EN difference is large. What happens when that difference is so large? Yes, no, somebody else. I know you know. You're doing great. What happens when that difference is so large? Somebody else. Who am I not picking on here? Come on, step up to the plate, somebody over here. What happens to electrons when the difference is so large? Yeah. They are transferred, yes? So you want to put here transfer of electrons. Yes? The electrons are transferred, right? Metals lose electrons, non-metals gain them. Remember that? Okay? Remember how to draw those? You should. You better. Okay? What's the difference here? What's the electronegativity difference here? It is what? Yeah. It's relatively small. Okay, it's smaller. Yes. It's smaller. You know, really technical terms here. Do we get a transfer of electrons? Yep. They share electrons. They share electrons. They share electrons. Huh? They share electrons. They share electrons unequally. right? It's dipole-dipole. So it's some part. The difference is this, right? Look, partial negative, partial positive, yes? A little bit of a negative end, a little bit of positive somewhere in a molecule. I don't know. It doesn't have to be a simple one. Somewhere, Mitch, somewhere there, yeah? This here, you better have positive ion, negative ion, yes? That's the difference between those two. It comes down to electronegativity, yes? Okay. What's next? 12? Did I give you 12? Okay. And we actually already talked about this, so you should actually know this one. How can a molecule with a polar covalent bond be nonpolar? Polar? Polar, yes. In fact, I'm going to tell you, almost every, look, the quiz we just had, every molecule on there has polar. This is, again, back to that definition. We've already talked about this. This is a polar bond, yes? This is a polar bond, and this cancels out that, yes, because they happen to be the same, right? Most molecules have polar bonds, CH4, polar bonds, altogether non-polar molecule. That's how most of them work. The only exception to that is going back to this. That's a non-polar bond and a non-polar molecule. FF, ClCl, BrBr, II, right? But most of the time they're polar bonds, yes? They just happen to cancel each other out. 13, here we go. This is riveting, isn't it? Hey, I'm really worried. I'm not gonna lie. What are we doing, A? I think we did A yesterday, but we're doing A. I think we're doing A, yeah. Okay. What's step one, if you're not sure? Step one is what? Huh? Say it proud. Draw them out. Yeah, you draw them out. If you're not sure, you better be drawing, okay? And I would suggest in this case, you probably should be drawing because we are not sure what's going to happen here, okay? Now, here's, again, some pitfalls that we run into, okay? Listen, I get this all the time. I get, oh, how are we going to compare these? Let's see. Size and shape. That's the answer to everything. We're going to start with size and shape. That's the bottom of the list, yes? That's the last thing you worry about. The other people say, well, this is F. This is F, so this is really electronegative, so it must be really polar. No. Okay? We start. Ionic. Are these compounds ionic? Either one. If they are, you're done. I'm probably going to guarantee you. Are they just metals? Are they molecular? Is there a hydrogen bonding here? Is H bonded to N? Now, you better check the other one. Is this hydrogen bonding? So this is dipole-dipole, yes? That's your winner, okay? That's not hard, is it? We have to be able to do that. I don't think that's too hard. You got to just follow the chart, guys. That's it. But you might have to draw them, okay? Next one. Which was the next one? C or Xe, okay? Again, are these ionic compounds? Am I comparing ionic stuff here, metals and nonmetals? No. Are these metals? No. They're over there, so no. Are they molecular compounds? Well, they're not really compounds, they're atoms, okay? Hydrogen bonding? No. Dipole-dipole? Is there a difference in electronegativity between, look, these are two different atoms, yes? We're comparing these two atoms. Is there a difference in electronegativity? No. So I guess now we're down to London forces. Now we can talk about size and shape. This one's bigger, has more electrons. Yes? That's your winner. London forces size. Okay? That's what you're doing here. What's next? E, right? Is that right? Okay. Another good one. Look. I'm going to actually draw that out, F2. Yes. Okay. Again. Okay. I'll draw this one out too. Why not? I don't know if we need to, but you might. Okay. Okay. Again, for the 100th million time, ionic, metallic, molecular, hydrogen bonding somewhere. Nope. Dipole, dipole. You got to know. Yes. X4, all the X's are not the same. This is polar. Remember, we just had a quiz on this. Dipole, dipole. That's why we had the quiz. Yes? Is it, what is this polar? Non-polar? London. Okay. Which one's stronger? This one is the winner, yes? Dipole, dipole compared to hydrogen bonding. You know why they gave you this, right? I'm just going to guess here, and I actually don't know if this is true because I should probably double check before I say this. Yeah, it's true because I kind of figured that was going to happen. But listen, why do you think they gave you these two? Because if you don't follow the chart and you get all the way down to, look, if you get down to London forces, size and shape, what do you notice about the two sizes here? How many electrons are here? 9 and 9, 18, yes? How many electrons are here? 6, 7, 8, 9, and 9 is 18, yes? Right? So then you'd probably go based on shape, yes? And if you go based on shape, which one would you pick? Spherical or kind of linear-ish? You'd probably pick that, yes? Right? That's not, we're not even there. You don't have to go that far because we already know that this is polar and that's not. This is permanent dipoles, temporary. This has got to be stronger, okay? So that's quite often why you get these questions here. You're going to find out that they're kind of have the same sizes and they have sometimes they have the same shapes. That's the point. What's next? Who? I hate G. C4H10, but Cl2. I don't know. What do you guys think? You tell me. Yep. Yeah, let's draw it. Or, okay. Now what? Yep. Why? So they're both molecular, yes. Hydrogen bonding, no. Dipole, dipole. We already talked about this as London forces, yes, the other day. If you don't know that, it is. We should know that. Nonpolar, nonpolar, both nonpolar, size and shape, yes. Which one has more electrons? Did you actually count them? Because they have the same, right? Don't they? This is what? 17 and 17, that's 34, isn't it? 17 and 17. 24 and 10 is 34. How convenient, yes? Okay. So that's what I'm saying. Like, if it comes down to this, you better, compare all aspects here. So it's not going to be based on size, is it? Because I don't know. I'd say you have to probably go based on shape. And I would say because this one's a little bit longer and more kind of spread out, I would say probably that one. Okay. That's what I'd probably go based on. That there. Okay. So again, kind of just a little, you got to be careful of those. C5H12 and C4H9, I think, right? Or NH3PH3. Which one? Did I give you that one? Okay. Yeah, NH3PH3, I think we know that's NH3, yes? Hydrogen bonding. But C5H12, and I gave you this one for a reason. This is a good one. Again, nonpolar. Yes, nonpolar, right? And we're going to compare that to this one. Now, a little bit smaller, you'll notice, C4H9. So that means I need 9 H's. I'll put 1 here, 2, 3, 4, 5, 6, 7, 8, 9, and then look what's left over, right? An F. Okay. Now, you should be able to look at those two and automatically pick out which one's going to be higher. Yes? Because what do we know about this? We already said this is what? Nonpolar? It's symmetrical, right? It's nonpolar. It looks the same all the way around. It's nonpolar. That's London. Does this look the same all the way around? No. In fact, remember, this is not the reason, but look, this is going to be a partial negative. I already know that because fluorine's going to pull electrons towards it, yes? It's highly electronegative, right? So that's not the answer. I'm just saying I know that automatically that's polar, yes? Because it's not the same all the way around. So that's polar and that's nonpolar, I'm going to go with polar. Dipole-dipole, yes? So I pick C4H9, F. This one. Yeah? Okay. Now, if you count up electrons, they're going to be the same again. Okay? So I just caution you on that. That's not the question, right? It's before that. We just don't go to size and shape all the time because it might be before that. Okay, what else is next here? What else did I give you on that list there? Anyone else? Who? N. Oh, yeah. And CLBR? Which one? Huh? Why? Yeah. Done. Ionic. Yes. The other one's not ionic. It's molecular. That's all you need to. That's it. Okay. You don't even. I mean, I guess you can draw them if you want to. You don't need to. Okay. Ionic versus molecular. No competition. What's next? L. Oh. That's kind of going to be, yeah, those are very similar for a reason here. NH2Cl and PH2Cl. Again, you should probably draw them. Which one's going to be stronger? Which one? Yeah, why? Hydrogen bonding, yes. Compared to dipole-dipole, yeah. Okay, again, that comes back to the quiz, yes. So you know that, then you know that that's hydrogen bonding, that's dipole. They're both AX3E, yes, et cetera, right? Polar, dipole. What else? Anything else? R? Okay. Oh, I gave you this for a reason. Again, I cannot stress this enough. Which one? Which one do you think? Which one do you think? Anybody want to disagree? Which one's stronger, this one or this one? You sure? Why would you say that? Yeah, PR's bigger. That's what we go based on, yes? Look, they're exactly the same. PR has way more electrons, way more. Not even like one down more electrons, way more electrons, yes? So that's the stronger one, okay? Has nothing to do with the F there. There's no hydrogen bonding. Yes, F is more electronegative, but I don't care, okay? We don't compare based on that, okay? I really hope someone says that in period 2 and, or no, we were in period 2. Hope someone says that in period 3 and 4. I hope so. All right, what else? Anything else? Do we kind of get the idea here? Are we good? Okay. Do you want me to do any other ones there? S and T, and you want to see those, I suppose, eh? Well, again, now when you get to S, I'd probably draw that out, yes? Because, again, right off the top, I'm like, you know, now it's C2F2, so that's going to probably look a little something like this. C, again, we probably want to take some time here and make sure we have the right diagram, I guess. And then we're going to have to connect those and those. I'm just going to do that if that's okay. I would never do that. You would never do that to me, right? But I'm going to do that to you. That's a triple bond, yes? Okay. C2F2. That's what it should look like, yeah? You can't put anything else in the middle. It's going to look like this. C triple bond, C, F, F. Yes? With 8 electrons, yeah? Right? C2F2. C2HCl. C's have to go in the middle. Right? Why do they give you these two to compare? Well, because they look identical, don't they? Again, you got to put the C's in the middle. You can't put H's there or CL's or F's. So they look identical. And why do they do this? Because they want you to compare them, basically, right? Based on, well, again, these are molecular compounds. What's gonna happen first here? Which one's the weaker one this time? Which one's weaker? This one or that one? This or that? This, that, this. Liam says this. Who said that? Anyone said that? Which one's weaker? This is weaker, yes. Why? Nope. Yep. This is nonpolar, right? Don't you think? I mean, look at it. Is it symmetrical? Yeah. Do you think that force is going to cancel out this one? It's linear, right? And those two will cancel out. Is this nonpolar? Do you think everything cancels out there? We have to look at symmetry too, like the whole picture. That's polar, isn't it? Guaranteed. In fact, I'll tell you this. That's the negative end. That's the positive, and I already know that. Because chlorine has a higher electronegativity, right? So probably going to look something like that. Okay. What's next? Who? Oh, we're going to go there already? Okay. Well, if you want me to do any other ones there, let me know. 15. 2 colorless compounds. One's ionic and the molecular. How are you going to determine which one's which? So I know we took a lot of notes, but basically this is where you got to shine here. Yep. No. Yes. I guess. Yeah. Just give me a second here. What are we comparing? Ionic and molecular. So you want to what? Whoa. You want to boil them? Okay, you can do that. Okay, that's good. You can boil them even before that. Maybe you want to, before we get too crazy here. No, before that. Not boil them, maybe. No, before that. You're on your chat. If you're boiling them, you're turning into a gas already. Let's maybe back up a step. No, before that. Melt them, okay? So you might want to melt them or maybe, I guess, boil them. That's an option. So melting points and boiling points is what you're going to use to help you decide between those two, yes? Ionic should be what? I'm not going to write this down because you know this. Tell me, though. Please yell it out. Ionic should be what? Yep. Yeah, and molecular should be lower. Yell it. That's your yelly voice? That's cute. Hey? Lower. Yeah. I like you. That's really cute. That's your yelly voice. That's at a -5 for me, just so you know. Okay. Yeah, lower. Molecular will be lower. Ionic's going to be super high, right? Now, use the right terms. We're going to use the right term, and we're going to say, what else could you do? Conductivity test. Now, does it matter what state we are in for a conductivity test? Yes. What if we're in solid form? What's that going to tell you? Yep. How would you decide between ionic and molecular if you're in solid form? Can you? No, right? So we can't talk about the solid form, but thankfully we've melted them. Perhaps. Now, if we're in liquid form for these two compounds, can you tell the difference? Ionic should be what? Very conductive, yes? Molecular is not. Okay, so we could do that. What else could you do? I forget what you said. What did you said? And I would say no, because the problem with solubility is ionic compounds can be very soluble or slightly soluble. Some molecular compounds are soluble. Like if you put sugar into water, it disappears because it's polar. Not for the same reasons, but just because it's polar. So that's going to be hard, and some don't. So that's really tough. The other thing that we talked about yesterday was you could hammer time them, yes? Put some parachute pants on, and let's rock it out. Can't touch this. Hammer stress. What happens with an ionic compound? How are you going to tell? Smooth plane, yes? Like charges line up and repel each other. Molecular. Soft, yes? So maybe you could check that out and see what happens with those, okay? Those are all good tests to do. All tests you should know about. Oh, I hope you guys are paying attention today. I picked these questions for no reason at all. Okay, if you had these two compounds, which one's better? Which one, basically they say, discuss the intermolecular and intramolecular forces. Well, intramolecular force, what kind of let's talk about that. What kind of intramolecular force do I have here? Nope, intra. And you would say, starts with a C. Intra starts with a C. O, covalent bonding, yes? What holds one of these molecules together? Covalent bonding, sharing of electrons. What is the intermolecular forces? What is it here? Hydrogen bonding. What is it here? London. Actually, draw them out. London. Carbons with a bunch of hydrogens. Okay, London. So obviously, which one's going to be stronger? Hydrogen, yes. Okay. Good. Which one has a lower one boiling point? Just be careful of that. Which one is lower? Well, it'd be C2H4. It'd be lower, yes. Okay, good. Yes? Okay. All right. Did I give you the other sheet for questions? Okay. Okay. Can you remind me here? So here's the deal. Just before, I don't need to record this anymore. You can just